Welcome back, Organic Chemist, round two. I moved a desk up here so I got a little bit of a shelf. I tucked my tie tail in so it hopefully isn't sticking out. And ideally I don't sound like an idiot, but if I do, please forgive me. I love you. Don't be so hurtful in those thoughts. Number 15, ladies and gentlemen, is where we're picking up today. And I think we'll go through 21. So 15 through 21. So first off, all classes of organic compounds that we've studied will have involved the concept of oxidation and reduction. If you remember from inorganic chemistry, with the exception of double replacement reactions, actually every reaction involves something being oxidized and something being reduced. Now, if you recall how we talked about acids and bases, remember we had an acid-base definition that was based on a compound, hydronium, acid, hydroxide production, base. Then we moved to the movement of a proton. Giving a proton, acidic, grabbing a proton, basic. But we said there's the best definition. This is chemistry, what we're studying. If we're studying chemistry, our favorite subatomic particle must play a role. And if we have a definition based on an electron, it is going to be the absolute best, most universally applicable definition. And then we said, okay, if it gives a proton, it would grab electrons. That's an acid. Acids grab electrons. That would mean bases give electrons. Well, acid-base reactions work great when you're talking about a specific solvent, water. But in organic chemistry, we often don't have polar solutions. We often don't need water to play a role. So oxidation and reduction actually fits really well as a tool for defining what type of reaction is taking place and what's likely to happen. So if we think back to that progression for acids and bases, compound, proton, electron, we're going to do the same thing with oxidation and reduction. Oxidation is the gaining of oxygen, hence the name, oxidation. Remember, Bill and Ted don't want you to be confused. So if something is oxidized, it gains oxygen. Well, if it gains oxygen, that's a specific kind of compound, O2. Then the next thought, if we think acids and bases, would be the proton definition. Well, if it's gaining an oxygen, we could also say oxidation is the loss of a hydrogen. And then lastly, let's define it on electrons. Well, again, it would be a lot like an acid then, if you're paying attention to this. It would involve the loss of electrons. Next up, we've got reduction. So reduction is not the gain of oxygen, rather, reduction would be the loss of oxygen. Reduction can also be defined as the gain of hydrogen, and it can also be defined as the gain of electrons. Remember, every time we have something being oxidized, we have something also subsequently being reduced. If you are having a tough time understanding what I'm saying, remember Leo? The lion goes grrr. Now, why did I say that and do that? I don't know. I'm crazy. Leo the lion goes grrr. Leo losing electrons is oxidation. Leo. The lion goes grrr, gaining electrons is reduction. So that's a simple way to remember our foundational particle, the electrons, which would be oxidation and which would be reduction. 16. The fewer hydrogens attached to a carbon chain, the more oxidized the bond. In other words, what I'm doing is I'm trying to tie in alkanes, alkenes, alkynes, alcohols, ethers, aldehydes, ketones, etc. So the fewer hydrogens attached to a carbon chain, the more oxidized the bond would be. Thus, an alkyne is more oxidized than an alkene, which is more oxidized than an alkane, because each of these is changing the number of protons, the number of hydrogens involved in the involved in the molecule, in the bonds for that carbon. 17. The removal of hydrogen from a molecule is a dehydrogenation reaction. High heat and a catalyst is often needed for this to occur. Think of propane. If I am removing hydrogens from that propane, isn't high heat and a catalyst, the spark, my push of the button, going to help that molecule change, interact with oxygen, and change from propane and alkane to CO2, significantly more oxidized, H2O, significantly more oxidized. 18. Dehydrogenation reactions are therefore going to be, well, let's think it through. I had propane. At my grill. I want to make some steaks. So I'm going to use this fuel and I'm going to oxidize it. I'm going to bring O2 to the table and I'm going to add a little spark. And that little spark is going to allow this oxygen to pull out its pistols and say, hey carbon, hey hydrogen, give me, give me, give me, give me. And what's going to be the spit out products? Two of them. CO2. Look how oxidized that carbon is now. Look at it. It's sharing a bunch of space with oxygens. And the other product, HOH. And again, look how oxidized my hydrogens are now. So this is an oxidation reaction. So even though oxygen has its pistols and is super aggressive, it still requires a little input of energy to make this change occur. A little bit of catalyst. So ethane would be the least oxidized, propane, an alkane. Ethene would be slightly more oxidized, and then the most oxidized would be ethyne, and that would be going through strictly an electron-containing situation. 19, hydrogenation. Hydrogenation. So dehydrogenation is pulling hydrogens off. Hydrogenation would be adding hydrogens in. Well, I'm adding hydrogens, isn't that the opposite of removing them? Well, if removing them was oxidation, then adding hydrogens, hydrogenation reactions, then those would be reduction. I'm reducing it. And this would also require a catalyst. This would be going from ethyne, which contains very few hydrogens, hydrogenate, to ethene, which contains two more hydrogens, boo-boo, to ethane, which contains, relative to my starting substance, significantly more hydrogen, specifically those two right here, those two right here, and my starting two, which would have been on my starting ethyne. Because remember, carbon in its forms, an sp3 hybridization is its max, right? It needs those hybridized orbitals to contain, so at most, it's always going to have 2 hybridized orbitals and 2 unhybridized in the p, which is what we talked about today in class if you were listening and caught that. So, number 20, oxidation organic chemistry is the driving force behind the conversion of one functional group into another. Because again, if we think this through, if we are changing functional groups, we are changing a very important component of a molecule. We are changing its concentration or the type of element that has an electronegativity. In other words, we're changing the number of electrons in a region. And if we're changing the number of electrons in a region, it's definitely an oxidation reduction scenario because Leo the lion goes grr. And so, if I am changing a functional group, I'm not necessarily going to be beneficial in classifying it as an acid base because acids and bases often involve hydronium hydroxide, protons changing. They often involve the aqueous solution. That's why it's such a great tool for inorganic chemistry. But it loses some power, some pizzazz, some explanatory capabilities when we get to organic chemistry, and we don't need that polarity anymore. And so we like the oxidation reduction. So now what we're going to do is 21, and we're going to go through a little bit of a thought, and then this will be our last note for the day, and then we'll pick up on Monday with 22. But 21 says, for example, we can convert an alkane, which is an energetic molecule, it is very reduced, into CO2, a very stable, boring molecule, by oxidizing the molecule through the addition of oxygen and the subsequent removal of hydrogen in alternating steps. In other words, let's pretend we have a grill. And it's a very specific, special grill. It's a grill that we can set where it applies just enough energy and just enough oxygen to ensure we have the least oxidized steps as we go from methane, highly flammable, to CO2 and H2O, the byproducts that aren't that intriguing. And so if I start with methane, which is CH4, and I oxidize it. There go those lights again. Sorry. And we oxidize it. We add O2. Well, when I oxidize methane, I'm adding oxygen. Well, the least, so this is now cane, the least oxidized next step would be to simply just add to this molecule an oxygen. And if I add an oxygen but do not remove a hydrogen, I'm going to produce an alcohol. And let's say this is the guy that got talked to. And now I've got the next step in terms of oxidation. Now what do I want to do next? Next, what I want to do is I want to do the next oxidation step. And this oxidation step is going to not be the addition of oxygen, but it's going to be another thought, which is the removal of hydrogen. So I'm going to pull off a hydrogen. Well, if I pull off a hydrogen, so let's see, removing a hydrogen, then what would I do? Then I would have that. Wouldn't I? If I pull off a hydrogen, I would have to pull off another hydrogen. So H2 would leave. Hydrogen gas would leave. And so now it's even more oxidized. Well, if I go one step farther, what would be the next step? So notice I added oxygen, then I removed hydrogen. Now I'm going to add oxygen again. My special grill is going to add just the right amount of oxygen. And if I add just the right amount of oxygen, but I don't pull off any protons, no hydrogens leave, I would then make a carboxylic acid. And this carboxylic acid would be methanoic acid. So I've gone from an alkane to an alcohol to an aldehyde, or a ketone, depending if I had a more complex molecule, to a carboxylic acid. And now I'm really close, because now if I go to that last oxidative thought, which is to remove the protons, and I look at this and I pull off that proton and I pull off that proton, so the protons leave. I'm oxidizing it by removing protons. I now have the lame, extremely stable, hard to remove, highly oxidized CO2. Now when we burn a grill, this doesn't happen because there's such an abundance of oxygen in that environment and there's so much energy and heat. It does not stop at these steps, and it goes all the way to CO2. Just like when we breathe in oxygen and our body enzymes take that oxygen and they plug it right into the simple sugars that we have, out comes water vapor, H2O, and the inert CO2. Students of Organic Chemistry Period 1, I love you, I miss you. I'm in the good life in Nebraska. Have a great Friday, Saturday, or Sunday, whichever day you're watching this, and I'll see you on Monday. Bye.